Hello. So I hope you hear me well. I'm Yaron. I'm a co-founder and CTO for a company called Equasio, which is developing solutions for accelerating machine learning and AI to production. What we're going to speak today about is how to build real-time machine learning pipelines in a simpler way than you would usually do. We have a packed agenda for those 45 minutes, I believe. We'll start with what are the real challenges in productizing AI and machine learning. We'll talk about MLOps and feature stores. Are they the solution? What are we talking about? We'll introduce an open source project that we've developed called MLRun that has those features built in. We'll go into a real-time churn prediction example to understand how do you model a problem, how do you break it into building blocks, and then sort of how you develop it. And we'll see a different demo of real-time fraud detection. We're using, again, machine learning models and real-time streaming data in order to detect a fraud and do some action based on that. So with that, let's first understand what are the real challenges when we want to move machine learning to production. And the key problem is that the research or the development environment is very different than the operational pipelines that we run in production. So you can see here the left side and the right side, where on the left side, this is typically how a machine learning workflow would look like. You know, you take some data, it may be like CSV files or some extractions from database or historical data. You run some analysis, using Jupyter, building aggregations and looking at the data, running some training in small scale, and then doing manual evaluation and so on. This is how you're building the model. As you go into production, the world looks a bit different. And first, you need to bring the data. And the data doesn't come from static resources like a CSV file. It may actually come from operational databases, and you need the ETL. It may come from streaming, Kafka, and so on. It may arrive from web APIs or any other APIs to external services. Once you bring all the data, you need to prepare that data at scale using different technologies, batch processing, stream processing, and so on. And as you do that, now you want to run a training on that data set. And even that training, you want to run it at scale across multiple algorithms, multiple parameter sets, with hyperparameters. You may need a cluster that, can run and work on all that large data as well as all the different permutations. Finally, you create a model. And that model needs to be running behind some real-time endpoints or even a stream and access the real-time features. And also that model needs to be monitored. So when we see that there's a drift or an accuracy problem, we have to retrain and build a new model and serve it and so on. We also need to integrate our model with different APIs. If we're building a web application or some event-driven application, it needs to integrate and interact with the model in order to bring real business value. And that flow is very different than the typical flow of taking your Jupyter notebook and building some model and then creating some report. Usually, in many organizations, this is done by separate teams. The data science teams may build a model in their notebooks, and then different teams of data engineers, DevOps, ML engineers, and so on will bring the right side. And this essentially brings a lot of complexity and slows down projects significantly. Sorry. So the key challenges that we have in operational machine learning are those that you see here. The first one we discussed is essentially working in silos. Different teams work with different tools. Some work with Spark, some Jupyter, some Kubernetes, deep learning and TensorFlow. Everyone has his own framework and his own ways to track experiment, to do CI, to do development, and so on. So we need to find a way to collaborate across. It's a very long process, as we've seen, and going to production is not just building the things that we mentioned. Is also for every component you have to think about packaging and testing and scaling and security and monitoring, logging, and CI and continuous deployment and so on. And that's a long process with a lot of development, a lot of testing. Another critical thing that we're going to touch upon here is how to access features. If you create features in the offline by just having a CSV, and now you need in production to create the features from a Kafka stream or from a transactional database and so on, that requires a lot of logic. There's also political issues around it. There's security issues. Who has access to that database? You don't want to interfere with the database, operational databases, as you do machine learning. So there are a lot of challenges that, because of that, you'll see that companies don't really have all the right features that they need in the production pipelines because of all of those reasons, the complexity and others. And finally, we have to think about the model accuracy. It's because you can train a model on some test data, but as you go into production and the data is different, the behaviors are different, your model is not going to produce the same results. We need to know how to monitor that activity as well as remediate, like do retraining, build ensembles, and so on. So the typical flow today in most organizations is what you see here. There is the research pipeline where someone throws the data into a data lake. Then you do all sorts of batch transformation, whether it's using SQL language or Python and pandas. You run some, you store the results in sort of a data set, a CSV, a Parquet file for training, and then you run the training. As you grow and you need stronger training, more scalable, more automated, then comes the machine learning engineers or the MLOps engineers. They take the code from data scientists, from the Jupyter, refactor it to run on a cluster, typically a Kubernetes cluster or on some cloud machine learning service. So that's the research pipeline. Now, as you finish with that pipeline, you go to a second pipeline where you build a more of an operational pipeline that taps into the operational databases, run online transformation. It's very different than batch transformations. So sometimes it's stream processing, it needs to work at scale, it needs to be partitioned, and so on. And then you store the results in some database for the scoring, and you run the serving. And finally, we also have the governance pipeline, which is where we track every activity in the model, the inputs, the outputs, the feature vectors, the latency, the performance, and we take that data, and this is how we analyze drift, accuracy problems. We may want to explain the results later on, so we may also do analysis on the data that was gathered from production. In most organizations, those are separate implementations done by separate teams and brings a lot of complexity and slows down the process. Also, again, a lot of delays because you're moving parts between one guy and another. You have accuracy gaps because the pipelines you're building for development, for building the model, and for using the models are different pipelines. And this really calls for a different architecture, and we're going to demonstrate how it works. But essentially, the general idea is to think more in a form of automation with everything needs to be automated into a production pipeline. So the first steps of development need to also be instrumented in a way that you can reuse that and not refactor and not redo your entire code. But also you need to think about the data as the centerpiece in that workflow. So this is really where you have the concept of a feature store. That was a concept that was originally coined by the big web providers, Netflix, Uber, etc. They all have their feature stores, and now there is more open source and commercial solutions which are feature stores. What is the feature store? Feature store is essentially a way to build and catalog features, but also not just to build and catalog features, also a way to describe the transformation, describe a recipe for building those features that will run automatically. What's also unique about feature stores is they know how to produce features for real time and for batch. So for training use cases, for serving use cases, and for monitoring and analysis use cases. All you're doing it once, and then it's used across every different application. So that's the general idea about that, and we're going to see how it's designed. What I'm going to show you is doing all of that with the framework, an open source framework called MLRun. And so you can just go to mlrun.org and see the architecture. There's a lot of documentation. The way that it works in order to automate all those pieces that we're seeing here is it has two underlying layers. The first underlying layer is the way to manage, catalog, and build features. This is through the feature store and connectivity to various data sources. The second thing that you have is a way to take a simple piece of code and run it as a fully managed service on Kubernetes with security, telemetry, auto scaling, logging, and so on. On top of those two baseline layers, you have different components that allow you to build the data ingestion pipelines, the training pipelines, the real-time production pipelines, as well as all the monitoring, and it's again fully managed with central metadata and orchestration. So you can go into the link and see. The core technology behind it is essentially serverless computing. What does it mean, serverless computing? One of the big challenges we saw in moving to production is taking a piece of code, building containers around it, scaling it out, addressing security, parallelism, and so on. So this is done automatically in MLRun. So the idea is that you can take a Jupyter notebook or some piece of code with a single command line, or a single Python command, you essentially make it a fully managed microservice that runs and scales automatically. It also extremely high performance because it has a lot of parallelism built into it. There are some benchmarks that were published in towards data science and other places showing how you can actually run your code faster. And also, as I mentioned, it's auto scaling. So one of the problems about data analytics, deep learning, machine learning, you want to run across multiple containers or multiple virtual machines. So those serverless functions are horizontally scaling. So they can run this against a much larger set of data and computation resources by distributing the workload in an efficient way. And you can also create those functions and store them in a marketplace, your own marketplace or a public marketplace, and reuse them in the pipelines. The other core concept we mentioned is a feature store. It's essentially a way to build those ingestion pipelines that will produce the features and persist the features in multiple mechanisms. For example, offline Parquet files used for training, or real-time NoSQL databases used for serving. But the pipeline is designed and defined only once. You don't need to do it multiple times, and we'll see a couple of examples of how you build those and run those pipelines. So once you build those pipelines, the features are generated along with all their metadata, with all their statistical information, and you can just go and choose those features from a catalog and then plug them into your training or serving workload with 2 lines of Python code. So again, a very easy way to build features and use features, and this is already ready for production without any extra DevOps, IT, engineering work. So let's take an example that, let's assume we want to build a real-time pipeline. And I take an example of real-time churn prediction. So let's assume you have a mobile app or a game or anything like that you want to create a pipeline that will predict the churn of a customer. Obviously, you can do that in batch. In many cases, churn problems are done on a monthly basis. You want to predict if someone is going to keep on paying. With this example, we also had a webinar on. Then you can see that you wanted to address the churn problem in a real-time fashion, because most gamers and most application users will churn within the first 24 hours. So we wanted to address that. So what is really the data that we can gather for such a mobile app? we have some static data about the users when they register, like the username, the birthday, geolocation or zip code, which can tell us some information about the social economical situation of the zip code and so on, affiliation, memberships, and so on. But there's also a lot of real-time data that comes in, like user activities. User goes and plays a game, goes and clicks a button, and so on. There are transactions, like user goes and buys credits or tokens, or pays a monthly bill and so on. And then maybe other types of events like social interactions. User does a like, user shares something. Social interaction can tell us something about churn of a customer. So let's assume we have all of that data and we need to build features. This is an example of the features that we want to build in order to train our model. And those features will be things that, for example, aggregate. Usually when you have real-time data, you want to build aggregations, like how many times you clicked in the last hour, how much activity, how much money you spent within a time window, and so on. So you can see that you can take those sources that I mentioned and build features. Now you need to join those features together into a feature vector, because each one comes from a different source, and they also need to be joined based on some timing information. Like I want to, if I'm looking at the transaction today, I want to also look at the activity of the user in the last hour relative to this point in time of today. So we need to do something called time traveling, is essentially join the different features based on timing information. So let's assume I want to build one of those lines, just one or two, couple of those lines, and the only tool I have at my disposal is SQL. So this is what it's going to take me to build a single feature. This is a real example of writing a select within a select, within a select to do time aggregation and things like that. It takes obviously a lot of time to run a single for a single feature, and that's very complicated. How many of you want to go and do all that coding? It's very slow, very resource intensive, because it's scanning the database multiple times and so on. And it won't work in serving, because in serving, when you're going to get the transaction from the wire, you want to immediately go and react, and you may get thousands of transactions per second. You can't run thousands of those SQL queries per second in a decent latency. So we need a different way. And there are different ways. There is something called the Kappa architecture, which is essentially processing the data as a continuous flow or as a stream. So typical tools in that will be like Spark Streaming or Apache Beam or Flink, or used to be something called Storm. No, not used too frequently these days. So you have all the information that you have that you want to build, all the transaction log as an example. We want to take that transaction log and essentially process it in two different ways. One is more as a cumulative processing, like a stream processing, and the other one is more sort of stored in a CSV or Parquet or batch files that would be used for some batch processing. So that's the general idea of how you do processing on real-time data. And this is also a slide from Apache Beam. Let's assume I have the customer data, customer transaction data, and the transaction user is the main key that we want to use for the feature vector. So what we typically do, we throw all those events. If we want to scale, we do something called sharding or partitioning, essentially divide the entire flow of data into partitions by users. And then we have some stateful processing of that. Why do we need stateful processing? Because in many cases we accumulate stuff. If we want to do average or sum of the transactions in the last hour, that means that we need to accumulate the transactions per user in the last hour or the last week and so on. So this is in general how you build stream processing, but this is very tedious, a lot of coding. By the way, usually in Java, most of those frameworks are Java frameworks, and if you're a data scientist, it's going to be very hard to build something like that. So part of Emerald, we built This is, by the way, called an actor model, this way of processing. We built a mechanism to run those pipelines in pure Python, very simple abstraction. And you can run exactly the same pipeline in batch or real time. So you implement it only once, and you have the same implementation for the training or the serving. So let's start with a simple example. Let's assume I have some CSV or Parquet file or a database that has some transactions. I want to feed them into this transformation pipeline and write the result into a CSV or Parquet file that will be used for training. So again, we can take and build a batch job that will take the source data, will run the transformations and store it. As we mentioned, we do need state to accumulate stuff, and we need to persist the state in many cases if we want to distribute the workload and handle failures and so on. So this is the baseline architecture. But let's assume we also want to do the same from a Kafka stream or an HTTP, then it could just work. We just need to change the way we feed the data and run the same pipeline. But in most cases, we want to have the data ready for training, but also for serving, or maybe even to build dashboards out of it, etc. So the only thing we need to add is essentially sinks, targets that will write the data in multiple formats that will be suitable for the different use cases. So that's the general idea of how to build a solution that takes that data, and we can feed any of those tables that I mentioned before. So we can take that data, feed it through a pipeline, and generate the results, and then use the results in the end. So, and this is much simpler, much faster, and much more scalable than the mechanism that you're using today. Now, the way that we want to also do it is in a way that is ready for production. And as you start developing with your native tools, whether it's a Jupyter Notebook or PyCharm, you can go and test it in a small scale, and then test it in a larger scale, and then go in a one-click deploy to production. So this is the overall theme of what we're trying to do with MLRun. Essentially, again, develop in your native IDE, get something working, test it on a bigger scale on a cluster, usually as a Kubernetes job or service. And then as you have that single thing working, you may want to create workflows which comprise of multiple steps. For example, in the batch side, you may want to grab some data, run training, run evaluation, do test deploy on the model, see it actually works. Or in production, you may want to have a pipeline like the one I mentioned before, of gathering, streaming data, aggregating it, doing some model inferencing, and so on. Now, everything that you're doing, you need telemetry. If it's the batch or the training side, you need experiment tracking and all of that. If it's a production side, you need to see things like CPU utilization, errors, failures, drift analysis, accuracy problems, and so on. So one of the nice things about this framework is that telemetry is built in. You don't need to do anything to see that it all works. And also everything is reusable. So as you build features or functions or models, you can just store them and then use them in a different pipeline. That's a general idea. And you can, again, go to mlrun.org. There's a lot of documentation and examples and notebooks that will show you how to do those things. One of the key features in MLRun is the ability to run real-time graphs. There are DAGs or graphs, certain pipelines focused on batch. There are many of those, like Kubeflow or Jenkins or CI tools and so on. But it's very hard to find a simple tool to build sort of real-time graphs. So in MLRun, there is a sort of something called a graph server that is used in different things. It's used for serving, it's used for ingestion, and for different tasks. And we can build complex real-time pipelines that span the data engineering part along with the machine learning part. So we can build a single pipeline, as you can see here, that starts from an event. The event could be a Kafka stream, an HTTP endpoint, a batch job, and so on. Run some enrichment, some pre-processing, some exception handling, go into a model ensemble that has multiple models that will be used for creating the result, and then some post-processing. So most serving engines, the only thing they allow you to do is create a model serving endpoint. But in real application, you need something more like what you see here in this diagram. And in order to describe this thing, it's just going and writing this piece of Python code, simulating it with a couple of lines of code, and when it's ready, just saying deploy, and that will build the entire real-time pipeline for you in a fully managed way on top of a Kubernetes cluster. This example, by the way, is also documented. If you go into demo run documentation, and you go into the serving and data pipelines, you'll see several of those. This is this example, which I mentioned. There's also another cool example of NLP pipeline, distributed NLP pipeline, that you can see, a paragraph, document processing, entity extractions, etc. So it's not really limited to machine learning cases. It also addresses deep learning and NLP pretty well. Now, once we build those pipelines, the next thing that we must do is also monitor the activity of our models and our pipelines. So the way that it works is, again, we have that feature store that stores all the features. The features also have a lot of metadata, all the statistical analysis of each individual feature. And we're going to see in a minute how we can actually use that statistical analysis information in our serving engine, which is very powerful for imputing, for value imputing. So we want to feed our model serving pipelines with those features that are coming from the feature store. Now, the model serving pipeline will write everything that happens, the incoming features, the outgoing features, sort of the predictions, the latencies, the performance data, into an output stream. And on that output stream, we have another serverless function, which is sort of built-in function that uses the same concept of stream processing to essentially produce the real-time analysis of the production data. And we'll see in a minute how it looks like, but essentially it analyzes drift and accuracy problems and custom matrix and so on, and writes back the production data into the feature store. So later on, when we want to do retrain, we can just trigger a retraining event, and it will upload and upgrade all of our models. So it will grab this. It grabs the statistical information from the feature store to understand the expected behavior of features, and it writes back all the feature real-time feature statistics and the feature logs, so we can detect drift and also do retraining and things like that. This is, by the way, a snapshot of, this is more like the built-in UI, and there's also a Grafana plugin. You can actually go by model and see the real-time production data. So again, very simple and intuitive. So with that, let's now go into a demo, and I'll share some notebooks. I'm taking an example of predicting financial fraud. Okay, so what we have in this example is 3 different data sets. So we may have user records, we have the account activities, log in, log out, and so on. We have real-time transactions, someone paid for something, and so on. We also have the label data, but what you'll see that we're producing few different feature sets from that. The transaction data is actually translated to 3 different data sets. One data set is the raw transaction data, the other one is transaction data by category, and the third is the labeled data, which could be essentially when you're doing the training, you can figure out the labeled data, like when there was a fraud from the transaction log. So as we go and ingest all of those different real-time streams into the system, it's going to be stored in the feature store. Then we can just go and do some interactive exploration on those feature sets and feature vectors. Later on, we may want to build a complete training pipeline that essentially takes a feature vector, creates a training set, run AutoML, deploy and test the model, and then deploy the production model, deploy the model into production. once you have the model in production, it works against the feature store to get real-time data as needed. And also, all the data is being monitored by the model monitoring piece and written back into the feature store, so we can do post-production analysis for like explainability and so on. So this is the entire pipeline I'm going to demonstrate. And again, a lot of those things are, you can look into the different feature store examples. There's like a stocks analysis demo. There's also like a real-time healthcare data analysis for like patient deterioration analysis, all based on real examples, real customer deployments. But let's go into the fraud example, which is slightly simpler. Let me zoom out a little, zoom in. Okay, so I want to build those pipelines that, again, usually I need data engineers and data scientists and DevOps and a lot of different people to build those complex features that I mentioned. So I'll try and do it in a single notebook to build all of those different features. I just need to like import and do some setup. Sort of for sake of the demo. Now I have some data. This is sort of we've taken some data from Kaggle and some other data that we have that has like monetary transactions. Okay, so and it's stored in our public data repo. So this is the example of this transactional data. Now we want to build a pipeline. In this pipeline, we also demonstrate how we build custom classes for the pipeline, but this is actually a library class which does data extraction. We want to take the timestamp and extract like time of day, hour of week, etc. So we can even implement like custom Python classes that will be plugged into the pipeline. And here we're essentially defining our real-time pipeline. This is the entire definition. There's no other code for it. So we create a feature set, which is essentially defining sort of a pipeline of creating multiple features. We define the entity, the source of the transaction. It also uses a column for timestamp, give it some description. And then we build a graph. A graph is sort of the DAG. You see, this is the DAG of computation. But the first thing we need to do is extract dates, hour and day of week. And then we may want to do some aggregations on 2-hour, 12-hour, 24-hour windows across the amount field. Okay, so this is the only thing we need to do in order to build that feature set, and we can ingest the data. We can ingest it from the notebook for sake of development, or we can ingest it as a real-time job or as a batch job with the change of a single parameter. We can also visualize our pipeline and visualize the data that is produced by our pipeline in the notebook. So we don't need to go and run some Spark and some other things and have data engineers, and they'll send us the CSV with the results, and then we want to iterate. Here we can iterate very quickly. We go change the code, change the pipeline, rerun. We see the result of our features. Now let's take another set of features, which is the activities. You see like user login, logout, timestamp, etc. And we build another pipeline here. We want to do one-hot encoding of the different activities like login, logout, and so on. So we just create a feature set. We define a pipeline that does some mappings and one-hot encoding on those mappings. You can see that this is creating the one-hot encoding with the result. Again, a few lines of Python code. Okay, and it's already ingested. When I say it's already ingested, then it's actually, if you go to the MLRun UI, you'll go into the, for example, transactions. You can see the different transaction, how to use this. You can see the different features, the transformation pipeline that we created, a preview of your data, all the statistical analysis of all the features, and so on. And this is done automatically the minute you've done this ingestion or preview. And now we can also build another type of data set, which groups the transactions by different activities, like someone buying something in the supermarket or buying some shoes and so on. We need to group the transaction because there may be an anomaly based on a category. If someone buying shoes 5 times a day, it's probably an anomaly. If he's going to the supermarket every day, it's probably not an anomaly. So we also want to group the results of based on some category and create a pipeline that will produce a feature set which is grouped by categories. And also the last thing that we may want to do is actually ingest the label data. And the label data, as I mentioned before, is derived from the original data, because there is a flag in the original data indicating a fraud. And we need to do things like potentially time shifting and other things on that data. So the last feature set that we created is the label feature set that stores like true or false if it was a fraud in the relevant timestamp. Okay, so this way we just created all those different feature sets. The next thing that we want to do is just create a feature vector. So we go and again build a feature vector, essentially saying, you know, we need all of those features from those feature sets. Give me a vector. This is the labels. This is for training. We can go and explore. You see, all those fields are joined automatically, and we can explore how our feature vector looks like, and again, iterate quickly on the notebook. Then we want to run training. So we use MLRun's ability to run automated jobs and scheduled jobs. So just giving it the feature vector as an input, telling it go training on multiple algorithms, because we want to do sort of AutoML. It will run, it will choose the best algorithm, provide us all the different analysis of the features of the algorithm, ROC curves, etc. By the way, again, if you want to see that in the MLRun UI, you just go and you can see the training jobs, you know, what was the source of the training job, the feature vector, the artifact that were produced by that training job, the results for every epoch or every algorithm, depending on deep learning or machine learning, and so on. So all that, again, was done automatically for you. You just said, here's the data, go run some library function that does training. And the last part is now going to production. This is usually a part where it takes at least 6 months to get everyone together and build a real-time pipeline with real-time data engineering and so on. So here I'm going to do it in a couple of minutes. We have a model serving class, which is essentially loading the model that we produced a minute ago. It's doing pre-processing. And what is done here in the pre-processing, in some cases, we get null values. Null values because the aggregates didn't aggregate anything, there was no transaction, or and we may want to substitute values from the real-time stream with some imputed values. So the feature vectors, they also store statistical information about every feature in the feature vector. So here, essentially what this code is doing is replacing null values with the mean values of that feature or with some other default value. So again, complex stuff, usually imputing and so on, you can do it in a few lines of code. But in the next version, all of that is going to collapse into the feature get function. So as I built it, now I want to build a pipeline. I don't want to just create a model endpoint. I want to build an ensemble comprising of the 3 of the models that I generated. AutoML generated multiple models, and I want to serve an ensemble of 3 of those models. So we can just go and build a pipeline, add a list of models. We essentially query the model database. We get the different models. We build a function with a for loop. We create a function with an ensemble router and multiple models. We create a simulator for our real-time pipeline. And we can just go, for example, to see how it works with the real-time features. I can just go and load the feature vector and do a get. Essentially, here I'm going to give you the ID of the user, and you give me all of the different features in the vector. So you see, with one command, I can just create a feature vector. Don't need any data engineering practices. Don't need stream processing knowledge. All that is happening for you. And if I want to test the simulated pipeline, I can just ingest a sample data and see the response. The response is the output is essentially 0, meaning there was no fraud on that transaction. If I want to deploy it into production, the only thing I need to do is just say deploy, and that brings containers and serverless functions on top of the Kubernetes cluster and giving me an endpoint to the real-time pipeline. I could use Kafka or Kinesis or HTTP to access that pipeline. And we can also test against the real. Invoke means testing against the real endpoint, and you can see it produces the same results. So you see, with 3 notebooks, I built something that usually takes organization 6 months to build because of all this automation and all this sort of serverless processing and feature store capabilities. So this is essentially what we've seen in the demo. I didn't show all the like fully automated pipelines, but this can also run as a CI pipeline using Kubeflow or other things like GitHub Actions or GitLab and so on. Just anyone that wants to, there is now an MLOps for Good hackathon that we're running together with Microsoft and supported by ODC and other organizations. It's about building automated sort of machine learning solutions for different good, things for good, like going to the link, all sorts of protecting kids and protecting against fraud and other problems, so people can join into teams and then make submissions. You could see judges from all, leading in the industry leaders in that space. So everyone is welcome for that. And also you can see a lot more content. We're running a bi-weekly webinar called MLOps Live, and there's a lot of different sessions from different companies and different individuals, leading individuals in the space. So with that, that's my session, and let's open it up to questions and see if you have any